Okay, so welcome everyone. Today, the speaker is going to be Francois Loeser from Sorbonne University, and he's going to talk about a motivic version of topological mirror symmetry. So, whenever you want.
Okay, thank you. It's a pleasure to give a talk in this Zoom seminar. So, I will present today joint work with Dimitri Viz. So, let me first introduce some of the objects we will deal with. So, we will consider Higgs bundle. In the following framework. So we will fix curve C. Say projective and of genus at least 2 over some field K, say of characteristic 0 of, for instance, a field of complex numbers. So Higgs bundle on C it's just a pair E theta, where E is a vector bundle on C, and theta is a morphism of vector bundle from E to E tensor with a canonical bundle on C. Okay, so this is a Higgs bundle. And we will consider two moduli spaces of Higgs bundle. So for this, we need to fix some line bundle on, say, L on C of degree D. And we consider the first moduli space we will consider is denoted like this. So it's a moduli space of semi-stable SLN Higgs bundle. So in the context of Higgs bundle, there are notions of stability and semi-stability, which exactly the same as for usual bundles, except that we consider only a sub-bundle for which the theta induces what you want. Okay, so and we have SLN Higgs bundle. I will say in 1 second that it is. And we fix also an isomorphism between the determinant of our vector bundle E and this guy L. And what do I mean by SLN bundle? Just that the trace of theta is 0. As a global section of the canonical bundle. This is a C. Okay, and so we will always assume that D and N are prime together. And so in this case, the moduli space is smooth and quasi-projective. So that's for the first of these two spaces. Okay. And the second guy is correspond to PGLN, which is a moduli space of a semi-stable PGLN Higgs bundle. And so I won't say what they are, but concretely, and this is what we will use here, is just a quotient of the previous guy by gamma, where gamma is just the n torsion of the pika group of the curve. So it's a finite abelian group. And so how do does gamma act on this guy? Just by tensorization, okay? Okay, and the geometric picture is, so so in the title I talked about, I mean, there is a notion of mirror symmetry, and here there is some duality between the two groups, SLN and PGLN. There are, one is a Lagrange dual of the other, and this is the key to what will follow. And so these two different moduli spaces are connected via the Hitchin fibration, because they have Hitchin fibrations on the same basis. So you may ask, okay, for here I have the superscript L, and here it's D. The point is that, in fact, one can check that this quotient is independent of L. So this is why I put D here. And so we have two Hitchin maps. But I will explain what they mean on the same guy. So the Hitchin maps just correspond to taking the characteristic polynomial of theta. So what is theta? Theta is an endomorphism of E, but twisted by the canonical bundle. So if there were no K, it would be just an endomorphism. So I could consider its trace is 0, and so all the coefficient of the characteristic polynomial. So the fact that trace is 0 is reflected by the fact that here it started at 2. And since it's twisted by k, I have to consider this guy here. Okay, so A is just a nice linear space. Now I have to introduce Hodgkin polynomials. So let's assume KC for simplicity. So consider the Hodgkin polynomial, I mean, of some variety capital X. Okay, and so it's just a kind of it's a generating polynomial of the it is a generalization of the Poincaré Betti polynomial. Okay, taking in account the hot filtration. But this Hodgkin polynomial is not enough for what we consider here. So when X is smooth connected, and I have, say, a finite abelian group acting on it, and preserving so I will define now the stringy Hodge polynomial. In fact, they are defined even if the group gamma acting on X is not abelian, but I will only need the abelian case, so I will only give the definition in this case. So it's a sum over the element of the group. Otherwise, in general, it's a sum over the conjugacy classes. And I have factor like this. And I have certain a polynomial. So what is this is just the fixed locus under gamma. So here I take the quotient, and so it's a combination of Hodge polynomials. But I have these factors here, which are something new coming in the picture. So if say it's not the same X, so say if Y is not good either, I'm sorry. Okay, so if X naught is in X and is fixed by gamma, W gamma is defined in terms of eigenvalues of gamma on the tangent. Okay, So I won't say more on these W's. They are called discrepancies. They also have some physical name, which I forgot. Is it bosonic shift or something like that? I don't know. Okay, so we have this stringy polynomial, which is in fact are connected with orbifold. Oh, sorry, with orbifold, the nature of this quotient. Okay, and it's not finished. There are not enough for what I want to explain. So consider the special case we are interested in. So this guy X with gamma as before, the n torsion of the peak zero. We have the Weil pairing. On gamma. So we can set, we have a character by just fixing putting gamma in the bilinear form. And okay, and this is the end of this complicated definition. So we have the stringy of the linear polynomial, and we can twist it by the character rho. And so there will be for this quotient. Okay, so it's stringy, so it's as before. And there will be something like that. And what is E with this character as exponent? It will be the E polynomial of some isotypical component of the cohomology of M. So let me maybe explain again. So this is usual stringy Hodge numbers. And here I twist by a character by so this is a fixed part, the fixed locus under gamma. And I have, of course, an action of capital gamma, and I can take the corresponding isotypical component of the cohomology. Okay, so that's enough for, that's all for preliminaries. Now I can state the first result, and I will explain I will give some motivation for these formulas, which may look a bit frightening at first. So there is a conjecture by Loeser and Thaddeus.
Sorry, Francois.
Yeah.
MPGLN on the left hand side, is it MSLN?
So yeah, I'm where?
So left hand side, so you wrote MPGLN, but it seemed good.
Yeah, it's this, yes.
So you define, so this twisted.
By definition.
Mhm.
It's by definition. Okay. I don't give a general definition. I just give the definition specifically in this case.
I see. Yeah, thank you.
So it's now a theorem by Groschenik, Wyss, and Ziegler. And it states the following. So it's relates the E polynomial of the moduli space of SLN X bundle. So it's a standard E polynomial because M is just a smooth variety. And it's just a matter of notation here as it's related to rho, let's say. Okay. And it's only inside here that the gammas, the small gammas appear. Okay. So now let me try to explain and maybe motivate a bit. So as I said, the two groups, SLN and PGLN, are dual of each other. So there is some duality. Okay, so in mirror symmetry, you relate Hodge numbers of dual objects. So it is what we have here. We have on one side the Hodge numbers of MSLN, and on the other side some kind of Hodge numbers for the other guy. So let me try to motivate why we have where we have this strange Hodge number. So the stringy part comes from the fact that this guy is an orbifold, or I mean a DM, a Deligne-Mumford algebraic stack. And the presence of the twist by rho corresponds to the fact that H on, so the two H vibrations are generically dual up to twist by some gel. Let me be more precise. So over some dense open say U in the etching basis A. The fibers of H and the dual fibration are torsors under dual abelian varieties. So, so the fibers are dual, except that it's only torsors. So there is some twisting, and the job corresponds to the connection between these torsors. And something important, since the cohomology of the two spaces on both sides are pure, we get an equality between Hoche numbers. So here we have three Hoche numbers. And this is a twisted version. This is a okay. So so this is the conjecture of Hauser-Tadeus, which is now a theorem by Goshnik, Wyss, and Ziegler. And before going further, some main ideas in their proof. So they use the two fibrations. Okay. So how can you compare polynomials? An idea is to compare number of points in finite fields on both sides. But the problem is that there is no control on the bad fibers. So I denoted by U the open set where you have dual fibrations. And the key idea is to get rid of them they use periodic integration. It is enough to get rid of the bad fiber. Okay, so
What's the meaning of the set of fibers?
I'm sorry?
What's the meaning of the set of fibers, right? What's that?
There are those outside U.
Oh, I see.
But I did not define U precisely, so.
Oh, I see. Mhm.
So you have
that's
control of the fiber over some big open set, but you really don't know what's going on the outside.
Maybe some bad fiber.
And you cannot you cannot connect the bad fibers on both sides.
I see. Okay.
So on one side, they compute honest volumes, periodic volumes. And on the other side, volumes of what? Of fibers. And on the other side, twisted or bifold volumes. These orbifold volumes, they are related to work of Denef and myself on the Mackay conjecture correspondence. And they explain the appearance of the integrals W gammas. Okay, but this is not the end of the story. So you compute some kind of volume of on fibers on both sides, and you want to prove that they're equal. So in the end, and that's the key of their proof, you have to compare the fiber volumes, and it's very much non-trivial. For instance, the volume of an H fiber could be 0 for just the stupid reason that there is no point, it's empty. You look at rational points to compute volumes, because it is empty. And the volume of the corresponding H hat fiber is 0 for a completely different reason, because a certain character sum is 0. You know, often character sums on groups and abelian groups are 0. Okay. And so here you see the situation is a bit is subtle, because you need to know that the volumes of the two fibers are the same, and in this specific case, which happens, okay, it's the case, but they are not 0 for the same reason. Okay, this can occur. So you really need they really need to work to prove this. So something non-trivial happened here. Now it's time for me to discuss the motivic version. Okay, so I will use consider Chow motifs. So I will denote by R the order of my group gamma. So I need to allow for R use of unity. So I denote by capital lambda the field generated by such roots. And I will consider the following category of motifs. So not to carry heavy notation, I just write it mod. And it will be the category of show motifs.
Order.
Show motif over K with coefficient in lambda. Okay, so the objects are defined over K, and lambda is for the coefficients. Okay, so this is the object that we will consider. So we consider the corresponding Grotten decree. Okay. So we denote by L the class of the left chest motifs. So the class of the motif of P1 is L plus 1. So to speak, L corresponds to the motifs with compact supports of the affine line. We will need to invert L and some other objects. So namely, we consider this ring. So it's here you can view L as just a formal symbol. No? And we will localize the quadratic ring, and so we will work in what I will denote like that, the localized quadratic ring. Just by tensoring with A over this polynomial ring. Okay, so this is the ring. So this ring here will be the ring where computation will take place. And now I can state the theorem. So which is very much the same. And here we have to take a stringy version and a twisted version. So this refers to and this refers to a twist.
Is the orbit for the motive is the same as the Deliman for Chow motive? Yes.
It depends how you define the Riemann-Factor motive.
Oh, okay. Okay. Sorry.
You have some definitions which are not good because you have to keep the group action by the gamma action.
Uh-huh.
So it depends very much on how you define things. Okay.
Uh-huh.
So in this ring.
I see. Okay. Thank you.
Okay. So that's a statement. And of course, one recovers result about Augereau polynomials by applying the morphism E, viewed as a morphism between rings. Okay, so now I will use the last 10 or 15 minutes to just explain some salient points of our proof. I guess you won't be much surprised if I say we replace periodic integration by motivic integration. So this is not so surprising, but the problem is that you have to make things work. Okay. So we use the motivic integration. In the form which I developed with Ralph Kluckers. which is more powerful than the classical theory. Why is it more powerful? Because it provides you a Fubini. But we use it for functions with values in this ring. But that's not a problem. I mean, the framework of Kleppers-Sandny allows you to do that directly. And so, as I just said, this is useful to use some yes, because we want to follow the similar strategy, that is to compare integrals on fibers of the two Hitchin fibrations. But then this they should give you at the very end the volume of the whole moduli space. And for this, you need some Fubini. So working with Chow motifs allows to consider isotypical components. For finite group actions. This is fundamental even to be able to state the result. And it's also very useful for several places, but one I want to mention here is it also allows to have a motivic version of the statement that non-trivial character sums, by non-trivial I mean involving a non-trivial character, on say commutative algebraic groups so when you do point counting of a finite field, this is useful. I mean, as I mentioned before, just you to compare two integrals which have to be 0. And this holds such a statement holds at the level of Chow motifs. Now, the strategy is similar to that of Grushnik, Wyss, and Ziegler. We express the equality we want to prove. As an equality between integrals, so in this case, motivic integrals, on moduli spaces of Higgs bundle, but now over the ring of Laurent of formal power series. Okay, that's a starting point. Now, in order to extract twisted string invariants, from motivic ones. I mean, from motivic volumes. We need some kind of equivalent volume formula for bifold. Now, applying Fubini, we reduce to an equality between fiber integrals. Outside some bad locus. Of course, the bad locus should be small enough to ensure that its volume, corresponding volume is non-zero, is zero, sorry. And so to do that, Groshnik, Wyss, and Ziegler in the periodic case relied on Tate duality. And so we replace Tate duality over QP, which is something with a strong arithmetic flavor, by the veil pairing of gamma. So on gamma, okay, then we need now to understand the interaction of the veil pairing with Néron models of so generic Hitchin fibers. So to speak, we replace the arithmetic used by the three guys by more geometry, and this geometry involves the study and the duality of Néron models. And this is fine because in fact, Néron models are extremely well suited for motivic integration. Okay, this can be already, this goes back to my work some time ago with Julien Sebat, where we study develop motivic integration on rigid varieties, and for this we use extensively Néron models. Okay, I think this is what I wanted to say. Maybe I'm a few minutes earlier than scheduled, but I think I'm done. Thank you.
Okay, so let's thank the speaker. If are there any questions?
Hello, Professor. Can you roughly explain why over the singular fiber the motivic volume is 0?
Yeah, so I mean, So the very basic, I mean, of course, this very simple observation is already used, for instance, in Batirev's proof of the fact that birational Calabi-Yau varieties have the same Betti numbers.
I see.
So the idea is if you compute volumes, you can neglect codimension 1 sets.
Oh, I see. Okay.
In fact, yeah, but you have to be more careful. I mean, it's of course what I just said is true, but you have to be careful. But this is a basic idea, and so this is very powerful because you see, if you with the method of the three guys, I mean, you will compare Hodge polynomials by comparing points in finite fields. But you cannot, if you want to use Hitchin fibrations, you can of course compare the points more or less on generic fibers. Maybe you can, but certainly you cannot do anything on bad fibers.
I see.
And of course, this a priori should make a difference for point counting. So there's no hope. But if you use integrals, then you can throw away these bad fibers, and it's enough to deal with these good fibers. So this is a very crucial observation, which was already used, as I said, but which I think is very, very powerful. And it explains why integration techniques are so useful in birational geometry first, and more generally, I mean, importance in this case. You see?
Okay, thank you.
Okay, any more questions? Well, then if there are no more questions, then let's thank the speaker for the nice talk.
Okay, thank you.
And yeah, I see some claps in the...
Yeah, by some good friends. I say hi to my good friends and to everyone. Thank you so much.
Okay. So goodbye, everyone. I will stop the recording.
Yes.